Hello, and in this video we'll take a look at A-level physics, specifically for EDEXCEL. We'll take a look at thermionic emission and particle accelerators in this video. So specification point 132 states that we need to understand that electrons are released in the process of thermionic emission and how they can be accelerated by electric and magnetic fields. And specification point 133 states that we need to understand the role of electric and magnetic fields in particle accelerators such as the LINAC and Cyclotron, and also detectors. And general principles of ionization and deflection are needed to be known. So what is thermionic emission? Basically, thermionic emission is the process by which electrons are emitted from a heated source. So let's say that external energy such as heat is applied to a given metal. Provided that the thermal energy is large enough, free electrons on the metal surface gain enough energy to overcome the attractive force of the atomic nucleus, and the bonds holding the electrons to the metal break, and therefore the electrons are released. And the electrons that have escaped the surface of the metal are referred to as thermions. And these free electrons are then accelerated by electric fields, which is set up due to a high potential difference. So these electrons would continue to move with a certain velocity towards the cylindrical anode. And beyond the cylindrical anode, since there is no electric field present, because there is no potential difference, these electrons would continue to move at a constant velocity because they experience no force. And it's important to note that in some cases, the electrons are made to pass through magnetic fields which would change their direction, so they would go towards a particular target. Moving on, we need to take a look at the linear particle accelerator, which is also commonly known as the LINAC. And basically, it consists of a series of tube-shaped electrodes that uses alternating electric fields, which is set up using high-frequency alternating power supply. And this allows for the electrodes to continuously change their charges. Therefore, this results in a changing electric field. So the charged particle is basically repelled from the previous electrode and attracted to the next one. And as the particle speed increases each time it passes an electrode, the lengths of those electrodes also increase, and this is to allow for the particle to spend the same amount of time in each electrode. High energy particles leaving the LINAC then collide with a fixed target at the end of the tube. Moving on, we now need to consider the cyclotron. So basically, the cyclotron is composed of two semicircular vacuum chambers. And basically a magnetic field is present which acts perpendicular to the electric field plane, and in this mid-region or this center space an electric potential difference is created, which therefore creates an electric field. Now let's say that a proton is placed into the semicircular vacuum chamber. When a charged particle is traveling into a region that contains a magnetic field, that particle will experience a magnetic force, and since the velocity vector is perpendicular to the magnetic field, the magnetic force will be perpendicular to both velocity and magnetic field. So therefore, the magnetic force will provide centripetal acceleration, so the magnetic force therefore allows the proton to follow a circular pathway when present in either of the vacuum chambers. And as the particle travels into a region where there is an electric field present, that particle will experience a force and therefore an increase in velocity. Now, when the velocity of a particle moving in a circle increases, its radius of curvature also increases, and this process would continue until the radius of curvature, velocity, and also the energy gained by the particle is large enough to leave the cyclotron. And once the particle has left the cyclotron, it can then go on to collide with a given target. So to recap this one more time, initially there is a charged particle at rest. In this case it would be a proton, and that proton starts to move in the vacuum chambers, and as stated before, the vacuum chambers are separated by a distance, and within that distance an alternating potential difference is created, which therefore creates an electric field which can accelerate the proton. The magnetic field present in the two chambers basically keeps the proton moving in a circular pathway, and as the velocity increases, the radius of curvature also increases. Once a proton has enough energy, it can then leave the cyclotron and collide with the given target. Thank you all for watching. I hope this video has been useful and cleared any questions anyone's had regarding thermionic emission and particle accelerators. Thank you all for watching, and goodbye.